Okay, so let me start off by thanking the organizers for putting together this very nice workshop and for inviting me to speak here. So I'm going to tell you about dispersion of collective modes in spinful fractional quantum Hall fluids. This is work done in collaboration with my graduate student Rakesh Dora, who's now a postdoc at IIT Bombay, and this is the main reference for this work. I'd like to thank generous funding from ANRF, and we'd like to make a special mention to the coding package diagram that we have used extensively for many of our numerical calculations. Okay, so the plan of the talk is as follows. So I'm going to quickly review fractional quantum Hall effect in the lowest Landau level. So we already heard Janendra speak about this yesterday, but it's going to be a lightning review. And there's going to be a twist in the sense that I'm going to add a spin degree of freedom to composite fermions. And as we will see, adding this spin degree of freedom adds to the richness of the phenomenology of quantum Hall effect. And in particular, I'm going to show that there is a new collective mode that emerges in spinful fractional quantum Hall states in the lowest Landau level. And that, it turns out, admits an easy description in terms of partons. And I'll end with some conclusions in Outlook. Okay, so the field of fractional quantum Hall effect started with this amazing discovery of Sui, Stormer, and Gossard, who took a two-dimensional system of electrons, placed it in a strong perpendicular magnetic field, and measured the Hall voltage and the longitudinal voltage. And what they found was that the Hall resistance was quantized in these units, h over 1/3 e square. So it's a famous 1/3 plateau. And concomitantly, they found that the longitudinal resistance vanishes as you go to lower and lower temperatures, which indicates that there is a gap state that forms. So fractional quantum Hall effect is actually fairly a difficult problem to tackle. And the reason is that it arises entirely from electron-electron interactions. So for a theorist like me, there is a nice ideal limit model in which you can work to describe the fractional quantum Hall states. So what you can do is you can take the cyclotron frequency. So in two dimensions, if you put electrons in a magnetic field, they form Landau levels. And the Landau level spacing is determined by this h bar omega c. So what you can do is take the limit where the mass goes to 0 or the B field goes to infinity. Then all these higher Landau levels become completely irrelevant. They are projected out of the problem. And then you have a partial occupation of the lowest Landau level. So here is an example of filling factor 2/5. So I have 4 electrons occupying 10 orbitals. And the Hamiltonian is fairly easy to state. Electrons are charged objects. So they just interact via Coulomb forces. So this is a simple Hamiltonian that one can write. So it's an extremely simple Hamiltonian to state, but very difficult problem to solve because we don't even know how to solve 3 particles interacting with each other. So what hope do we have of solving so many particles interacting with each other? And quantum mechanics in this problem is built in this fact that once you project to the lowest Landau level, these particle coordinates don't commute anymore. So xi and yj has a commutation relation which is I times L square, where L is the characteristic length scale of this problem, the so-called magnetic length. But what experiments are telling us is that interaction is somehow picking a unique state, gap state from this highly degenerate manifold. So how do we make any progress at all? So the first step in this direction was made by Laughlin, who essentially just guessed an ansatz for the 1/3 state. So what Laughlin assumed was that electrons are correlated in this Jastrow form. They are pairwise correlated. And that helps minimize the Coulomb repulsion because it keeps electrons away from each other. And he just basically wrote down this wave function, product I less than j, zi minus zj to the power m. And z here is the two-dimensional electron parametrized as a complex number. And it turns out that this just product I less than j, zi minus zj is also the wave function of one fill Landau level. So I'll also write this as phi1. And because we have fermions in the problem, m has to be an odd integer. So if you take m to be 3, then that describes the plateau that was observed at filling factor 1/3. So in general for fermions this m has to be odd, and for bosons this has to be even. Laughlin actually also went on to show that if you look at excitations of this system, so-called quasi-holes and quasi-particles, that actually carries fractional charge. So if you look at this system, this has particles of charge E over m. And then Arova, Schiefer and Wilczek showed that this fluid is even more exotic, that if you take 2 of these particles, 2 of these Laughlin quasi-holes and braid one around the other, then you pick up a phase which is like 2 pi by m. So you get fractional statistics in the problem. So this is all about the ground state and charged excitation. So what about neutral excitation? So one way to construct neutral excitation is to take an equal number of Laughlin quasi-holes and quasi-particles. But another way was put forth by Gerwin, MacDonald and Platzman, who showed that you can construct a wave function of this form where you take the density operator. So the density operator has one C dagger and C, so it does not add any charge to the system. And you act it on the lowest Landau level ground state. And because you always want to remain in the lowest Landau level, you just project the density operator to the ground state, or you project this whole thing back to the ground state. So this rho q is the lowest Landau level projected density operator. This goes by the name single mode approximation. And you can compute the gap of this excitation from just the correlations in the ground state, because all the input that you need is that of the density correlation of the ground state, so-called structure factor. And from that, Gervin, McDonald, and Plotzman computed this gap. And this gap typically looks like this. So you have a minima, and then it goes up like this. And in analogy to the spectrum that Feynman had obtained for helium, they dubbed this mode the magnetoroton mode. So it's a roton in a magnetic field. So this is the Laughlin ground state, and you typically get this sort of spectrum. And experimentally, this has been observed in light scattering experiments, most notably by Aaron Pinsuk. But very soon after Sui, Stormer, and Gossard's experiment, better samples were built, people went to much larger fields, and they saw a whole zoo of fractions. And these fractions primarily lie along this n over 2pn plus minus 1 sequence. So this is 1/3 that was first seen, then 2/5, 3/7, 4/9. And for all of these states, there is a partner states which are at like these hole conjugates. So in the lowest Landau level, you have this symmetry called particle hole symmetry. So you can exchange the state of electrons to a state of holes. So that maps a problem at filling nu to a problem at filling 1 minus nu. So you have a partner state of 2/3, which you can view as 1/3 Laughlin state of holes and so on. So we will only concern ourselves with filling factor that's less than equal to half because of this. And the interesting thing is that you can't go and put like 5/2 or 7/3 in Laughlin's ansatz, because then the wave function is not single valued anymore. So again, we are kind of stuck. We don't know how to understand these other fractions that were seen. And the key insight came from Janendra, who postulated this idea that the fractional quantum Hall effect of electrons can be understood as the integer quantum Hall effect of some other objects, some emergent objects which are called composite fermions. A composite fermion by definition is a bound state of an electron and an even number of vortices. And in many contexts, you can view the vortex as also a flux quanta, because if you go around a vortex, you pick up a phase of 2 pi. And the same thing happens if you go around a flux quantum. So you can think of the composite fermion as being a bound state of an electron and an even number of flux quanta. So in this schematic, I show the golden path in going from the integer Hall state to the fractional Hall state. So let's say you start at filling factor 1. So filling factor 1 means you have 3 electrons in like 3 flux quanta. And to each of these electrons, you now bind 2 fluxes. So that turns them into composite fermions. And you slowly smear out this flux quanta and merge it with the external magnetic field. And in this process, you kind of hope and pray that the gap does not close, because you want to adiabatically continue from the left side to the right side. So this is a problem we understand: integer Hall effect, non-interacting electrons. And this is the hard problem that we would like to understand: fractional Hall effect, interacting electrons. And if you can adiabatically continue from the left side to right side, there is some hope of understanding this. So I'm going to assume that this adiabaticity holds. And for all the states that I'll talk about today, this assumption is going to hold. So now what you can do is run the tape backwards. You take electrons in much larger magnetic field. And from this external magnetic field, you capture 2 flux quanta and bind them to each of these electrons to turn them into composite fermions. And to the 0th order approximation, you assume that composite fermions are non-interacting. And now, just like electrons in a magnetic field form Landau levels, composite fermions in this residual magnetic field that they see form their own Landau-like levels. So these are called lambda levels. And whenever an integer number of these lambda levels are filled, you get fractional quantum Hall state of electrons. So this mapping allows you to map quantities of electrons to quantities of composite fermions. So all the star quantities here are quantities for composite fermions. So the effective magnetic field seen by composite fermions is the external magnetic field minus the 2p fluxes that you bound to each of these electrons. So that then allows you to relate the filling factor of electrons to the filling factor of composite fermions. And you get this famous Gen sequence of states. So nu is nu star over 2p nu star plus minus 1, and whenever nu star is n, you get this n over 2pn plus minus 1 sequence, which is precisely the most robust sequence that's seen in the lowest Landau level. Okay, so what about excitations? So this analogy to integer quantum Hall state essentially just pulls out everything for you. So let's take an example of filling factor 2. 2/5. So 2/5 state of electrons maps to 2 fill lambda levels of composite fermions. So whole excitation here would be an empty electron or an empty orbital in the nu equal to 2 state, and that maps to a composite fermion hole excitation. And particle excitation in the same language will be like an extra electron in an otherwise empty Landau level, and that becomes like an extra composite fermion in an otherwise empty lambda level. And now if you put these two things together, you get an exciton in the integer language, which now becomes like a composite fermion exciton in the fractional language. Okay, so I told you about some qualitative stuff of composite fermion theory. One can ask, can we get some numbers out and test whether this theory is actually accurate? And you do that by again constructing these Jan wave functions at filling factor n over 2pn plus minus 1. So the idea is fairly straightforward. So you first construct an integer Hall state of electrons. So this is a slated determinant state. We know exactly how to construct this. So that is written as phi plus minus n. And to turn them into composite fermions, you multiply by this Laughlin-Jastrow factor of product I less than j is zi minus ej to the power 2p. So this attaches 2p vortices to each of these electrons to turn them into composite fermions. And because we would like to work in this ideal limit where the magnetic field is sent to infinity, I have to brute force project this state to the lowest Landau level. So that's it. That's the wave function, the Jan wave function for filling factor n over 2pn plus minus 1. So a couple of amazing things to note about this. So first, usually the way we construct wave functions is put in some trial parameters in them, some variational parameters in them, which you then optimize to then minimize the energy or maximize overlap with an exact state. But here it turns out the moment you fix the numbers on the left hand side, everything else on the right hand side gets completely fixed. So there's no like wiggle room. So there are no adjustable parameters in this. And a thing that's somewhat technical but would be useful for us is that this projection can actually be done for very large sizes. Okay? So you can actually get thermodynamic limits very accurately by constructing these wave functions and computing properties for them for fairly large systems. Okay, so I'm going to use the spherical geometry to test and show how well these wave functions work. And the reason for doing that is I'm mostly interested in bulk properties. So unlike in the disk where you need to put a confinement to keep electrons within some radius, the sphere is a nice compact geometry and it has some nice features. So appropriate to this geometry, the orbital angular momentum and its z quantum number are good quantum numbers. So what you do is you get hold of a magnetic monopole, you place it at the center of the sphere, that's shown in this yellow, and this generates a radial magnetic field through the surface of the sphere. So it's like the disk now wrapped up on the sphere. And the flux quantum and the number of particles are related by this relation, and that relation has a nice quantum number called the shift, which can actually be used to characterize the state. And the other ingredient we need is this idea of Haldane pseudopotentials, which parameterizes the interactions. So what you can do is you place two electrons in the lowest Landau level and ask what is the energy cost of placing them in some relative angular momentum state. So we're always going to look at interactions that are spherically symmetric. So they can always be expanded in the basis of relative angular momentum. And these Haldane pseudopotentials tell you what is the energy of placing two electrons in some relative angular momentum m state. And for the lowest Landau level, they decay in this typical fashion, in this 1 over r fashion. So when they are very close together, you have huge penalty, and then they typically decay. And for fully polarized electrons, the only pseudopotentials that are actually relevant are the odd pseudopotentials, because fully polarized electrons can approach each other only in odd relative angular momentum. Okay, so with these ingredients in place, we can go ahead and do the computation. So we compute what is the overlap of the composite fermion state with the brute force exact projected lowest Landau level Coulomb ground state. And the numbers that you find are really high. So for example, for filling factor 1/3, you can do this computation for about 15 particles. So that has a Hilbert space of about 2 billion. And the overlap of the Laughlin state with the exact Coulomb ground state is like 99%. I mean, if you pick up a random state of this Hilbert space dimension and take its overlap with the Coulomb ground state, it will essentially get 0. So the Laughlin wave function does not just captures the right universality class, it's like capturing the ground state microscopically accurate. And the same is true for the Jan wave functions also. So for example, at filling factor 2/5, if you look at 12 particles, the overlap of the Jan state with the Coulomb ground state is like almost unity. Yeah. So these wave functions are very good to even do like microscopic calculations and then compare against experiments. So how about excitations? So here's a spectrum for filling factor 1/3. This is the largest system that we can do for filling factor 1/3. It's about 14 particles. And these dashes are obtained from exact diagonalization. And these dots are obtained from composite fermion theory. So the ground state is just the Laughlin state, and its energy agrees with the exact energy to like 4 decimal places. So that's how good an agreement you have. And important thing to note is that in each of these angular momentum state, you have like about 100,000 states. And in some of them, you have like million states. So this dot is able to capture the exact overlap or exact coefficients, about 1 million coefficients almost exactly. And all of this is without any variational parameters. So the first branch of excitations is this composite fermion exciton. You have a particle whole pair of composite fermions. And that again captures this mode that is seen in exact diagonalization very, very accurately. So the dots and dashes are almost right on top of each other. And this is like a superposition of like 2 million states. So we had two ways of constructing the neutral excitation. We had this Gerwin-McDonald-Platzman recipe, and we had this composite fermion exciton. You can ask which works better, which one should I use? So generically, the composite fermion exciton is much more accurate than the Gerwin-McDonald-Platzman ansatz. So generically, the CF E is much better than the GMPs. So that's illustrated in this plot. So these are the exact diagonalization results, and these blue circles are composite fermion exciton results. And this GMP mode is these green diamonds. So the GMP mode goes far away as you go to larger wave number. But it turns out that if you look at the smallest wave numbers, if you look at the long wavelength limit, then for the primary Jan states, this n over 2 n plus minus 1 Jan states, the composite fermion exciton and the GMP are nearly identical. Actually, for the Laughlin state, they are exactly identical, but for like 2/5, 3/7, and so on, they're nearly identical as Q goes to 0. Okay, so now comes the idea of adding spin to the problem. So if you now add spin to the problem, new collective modes become possible. So in the old version, you had to take the composite fermion from the 0th lambda level and put it in the first lambda level. But now let's say the Zeeman energy is really low. Then another lambda level comes into the picture, that's the 0 down lambda level. And you can create a collective mode where you take a composite fermion from 0 up lambda level and you can put it in the 0 down lambda level. And that gives a dispersion which is like this, which is drawn in these green dashes. This is just exact diagonalization data, and this red squares are this excitation's energy. And this energy is lower than the charge gap. So if you do now transport at small Zeeman energies, this is the mode that actually you will pick up. There's also a way to construct the spin wave ansatz from the density wave type of approach. So you now take the density wave corresponding to spin flip and act it on the ground state. And this state actually again agrees with the composite fermion exciton in the long wavelength limit, but it does not agree once you go to like larger wave numbers. So there the density wave ansatz just goes somewhere completely different from where the actual mode lies. But in the long wavelength limit, it does agree with the CF spin wave ansatz. Okay, so now one can do this thing for other fractions. So you do this at like filling factor 2/5, 3/7, and so on. And one finds something very interesting. There is actually a spin roton instability for states at n over 2 n plus minus 1 for n greater than 1. This was pointed out by Mandal and Jain about 2.5 decades ago. So what they did was they computed the energy of this composite fermion spin wave ansatz, and they found that this has an energy that's lower than the ground state energy at some q. Okay, and if you are really at 0 Zeeman energy, this will be an instability of the ground state. And a way to think about that from the CF picture is that in the fully polarized 2/5 state, you have two full lambda levels. You fill 0 up and 1 up. But now what you can do is you can lower the CF cyclotron energy by bringing 1 up down to 0 down. So this gains in h bar omega c star for you. And only because of Zeeman, this is not usually an instability of the fully polarized state. But if you set Zeeman to 0, this will be unstable. And the same thing happens for 3/7. So if you look at 3/7, there's an even deeper roton minima that you observe. And this again, you can understand why it's deeper, because now you're going from 2 up to 0 down. So you gain in 2 times the CF cyclotron energy. And these spin roton instabilities actually tell you that with spin in play, you can actually get new ground states. So this 2/5 ground state will be unstable to that new ground state. So what are these new ground states that you can now start getting? So at 1/3, it turns out that you still keep getting the Laughlin state because that's a quantum Hall ferromagnet. So even at 0 Zeeman energy, the best ground state that you can write at filling factor 1/3 is the Laughlin ground state. And this is spontaneously polarized. So because of interactions that the ground state is spontaneously polarized. But at 2/5 now you have the possibility of occupying 2 Landau levels, but these 2 Landau levels can be of opposite spins. So instead of occupying 0 up and 1 up as we were doing before, you can now occupy 0 up and 0 down. So this is a so-called spin singlet state at filling factor 2/5. And for example, now if you go to 3/7, there are some possibilities that arise. So you can now occupy 2 of the up Landau levels and 1 of the down. And if you now go at like 4/9 and so on, there are 3 states that are possible. You occupy 4 of up, you occupy 3 of up, 1 of down, or you occupy 2 of up and 2 of down. So with spin, there are many new ground states that are possible. And because of that, these new ground states also host some interesting spin modes. So firstly, multiple density wave excitations can now arise in these states. So I'm going to now restrict myself to just spin singlet states, and particularly to this 2/5 spin singlet state that we saw. So here multiple density modes can arise because you have now 2 kinds of density operators. You have a density operator for the upspin and you have a density operator for the downspin. And what you can do is you can look at the symmetric and antisymmetric combination of these. So one combination is the symmetric combination, which I call the symmetric density wave. So you take rho bar up plus rho bar down. And this is actually exactly the operator that GMP had in mind. This is just the total density, and you just apply the total density operator on the ground state. And the nice property of this mode is that it actually has the same spin as the ground state. So if you act it on a singlet state, it has exactly, it is also carries s equal to 0. And then there is another combination which is called the antisymmetric density wave. That is, you take rho up minus rho down and you act it on the ground state. And it turns out that this excitation has spin that's different from the ground state. It has actually spin s equal to 1 for spin singlet ground states. Okay, so this was the density wave construction for collective modes in spin singlet systems. Now we go to the composite fermion theory and ask what are the modes that you get from the composite fermion theory, and that actually kind of mirrors what we just saw. So you again have symmetric composite fermion excitons and antisymmetric composite fermion excitons. So what you do in symmetric composite fermion exciton is you take the symmetric combination of 0 up to 1 up with 0 down to 1 down. So you just excite the composite fermion to the next lambda level, but now you have to do it in a symmetric way where you take this for the upspin and the downspin and you add them in the symmetric fashion. And the antisymmetric composite fermion ansatz is you take 0 up to 1 up and 0 down to 1 down, but you take the negative in between. And this you can show it has spin s equal to 1 and this state has spin s equal to 0. Okay. So when we computed the energies of these modes, we found something really puzzling. So first, let me just say that the composite fermion exciton mode agrees beautifully with exact diagonalization. It's not surprising. So the ground state agrees well, the excitations agree very well. But it turns out if you look at the GMP mode, it's completely off from the composite fermion mode. So if you look at the symmetric density wave, that has very high energy compared to the composite fermion exciton. And this is true even in the long wavelength limit. So at least what we were seeing previously was that the density wave ansatz is off from the exact and CF ansatz. But at least in the long wavelength limit, the two used to agree. But here, even in the long wavelength limit, it's completely off. So the GMP mode is just somewhere else. And this kind of tells us that if you, let's say, look at the dynamical structure factor, which is the spectral function for this density operator, then it has to split into at least two modes. So one will be this mode, and there has to be some higher energy mode because the weight of the GMP has to be distributed at two places, so that that mode plus this mode together will give you this density ansatz. But the puzzle is what is there, what other mode can exist in these states. So what we do to figure that out is to go to the parton theory. So the parton theory was again introduced by Jain as a generalization of his composite fermion theory. So the idea in the parton theory is you take the electron, you break it into some fictitious particles called partons, and you place each of these partons into some integer Hall effect state and you fuse them back together to recover the electron. So that gives you wave functions of this type. You take products of integer Hall states, and the important thing is you have to take an odd number of them to maintain fermionic antisymmetry. And because I work always in this limit where the magnetic field is sent to infinity, you project this state to the lowest lambda level. So to be able to put a parton at this filling, the charge of the parton has to be related to the charge of the electron by this relation. That is because each of the partons is also seeing the same field as the electrons, and they are also at the same density as electrons. So their charge has to be changed to make sure that they can make sure the flux quantum is changed and then they can fill some other filling. And then the sum of the charges of the partons has to add back to give you the charge of the electron. So that relates the filling factor of the electron to the filling factor of the parton. So the picture to keep in mind is the following. You take an electron, you break it into some fictitious objects called partons, and you fill integer number of these partons. So let me give you an example of parton state. So the Laughlin state is a parton state. The Laughlin state is a 1-1-1 parton state where all the partons fill filling factor 1. So this is probably the simplest way to see that the Laughlin state carries fractional charges. Because if you now go back and look at what is the charge of the parton, then filling factor nu is 1/3 and n alpha is 1. So you have 3 partons, each filling 1 lambda level and each carrying a charge E over 3, which put back together gives you the charge of the electron. The Jain composite fermion states are also parton states. So they are n1-1 parton states. So now the partons are different. There is one parton which fills 2 Landau levels and there are 2 partons which fill 1 Landau level. That now gives you different charges. There is an E over 5 parton and there is a 2E over 5 parton. Okay, so with that thing in place, you can now actually answer this question. So one can write down trial wave functions to capture the ground and excited states at filling factor 2/5. So firstly, let's go to the ground state. The ground state is fairly straightforward. You take wave function of nu equal to 2 singlet, which I write as phi 1 up, phi 1 down. And to that, you multiply by phi 1 square, which is this Laughlin-Jastrow vortex attachment to turn the integer Hall state to CF state. The low-lying composite fermion exciton mode is you just take the integer Hall state at nu equal to 2 and you create a symmetric exciton in that. That's the standard composite fermion exciton. And a slightly better version of that can be written out by pulling one of these factors of phi 1 out. Because that then ensures that no two particles, irrespective of their spin, can be right on top of each other. and that helps in minimizing the Coulomb energy. So this state is called the hardcore projected composite fermion exciton state, and that has slightly better energetics than this state. And now the wave function of the parton mode can be easily written down. So the wave function of the parton mode is now you create an exciton in this phi1 factor itself. So usually in the composite fermion theory, the vortex attachment factor plays no role. It just stays silent. But what we are proposing is that the vortex attachment has dynamics of its own, and you can create an exciton in the vortex attachment factor. And that will actually explain this extra mode that we saw. And a wave function for that can be written down because this is just phi1 exciton times phi1 comma 1 comma phi1, and that is just factorizes into nu equal to 2 singlet times the bosonic Laughlin GMT exciton. Yeah, I'll just finish. So yeah, with that in place, you can show that this extra mode actually has higher energy, and the GMP mode is actually splits exactly into these two modes, and everything kind of matches out. So if you compute the dynamical structure factor, the dynamical structure factor is exactly the sum of these two modes. Okay, so let me end with conclusions. So there are some very high energy excitations in the Jan states that actually happen to lend themselves to a simple description in terms of partons. So central prediction of our work is that if you do light scattering at filling factor 2/5 in the singlet state, you should see two collective modes. That will be in contrast to what you would see for the fully polarized 2/5 state, where you will see only one collective mode. Okay, so with that, let me just stop, and I'll be happy to take questions.
Let's have the speaker for the next talk. Questions?
Short question.
Okay.
What are spin one collective mode?
Yeah, that is also there.
Can you, is it there? Where is it?
So that has exactly, that is also gapped. So it's there in our paper. I don't have a plot of that, but it's also gapped because the 2/5 singlet is a gap state. It has slightly lower energy than the symmetric exciton state.
Fascinating analogy with benzene. You take benzene.
Yeah.
First excited state is a spin triplet.
Yeah.
Why said that energy is spin singlet?
Yeah, it's kind of similar. I mean, I don't have the exact energy, but it has lower. The S equal 1 has lower energy than the S equal 0.
Yeah, I have a very naive question. First of all, I enjoyed your talk. So I'm just trying to understand, as an outsider to this field, like you have with both the integer quantum Hall effect and fractional quantum Hall effect together. So how come if you say some of the magnetic lines are attaching to an electron, that the flux will overall reduce, right? In that case, how can you explain the integer quantum Hall effect? Like because they are kind of gradually increasing with the expected.
So in the integer quantum Hall effect, you have exactly the same number of flux lines as electrons.
So how can they coexist? Because if one of them...
They don't coexist. They occur at different parameters. So the integer Hall state occurs when the number of fluxes is the same as the number of electrons. And the fractional Hall state occurs when, let's say, 1/3 occurs when the number of fluxes is 3 times the number of electrons. So you need many more orbitals to create fractional Hall states.
More questions?
So does this also manifest in terms of, let's say, spin static structure factor? You would see some sort of spin configuration.
Static structure factor, I don't know, but if you compute the dynamical spin structure factor, you will see it. So if, let's say, you compute the dynamical structure factor with this, as your operator.
The question is, do you see like a manifestation of a local moment that is arising because of this?
There is no local moment because this state has the same spin as the ground state.
Okay.
Yeah. It is not in the real spin in that sense. But let's say if you now compute the dynamical structure factor with this operator, you will see weights at 2 places. And those 2 places will be actually very close to these two energies. The energy of this and the energy of that.
Just a continuation of the question. So suppose you plot the spin density. As a function, in this droplet type of picture. So you would see a oscillation in the...
No, the ground state droplet has nothing, right?
No.
For the excitation you will see some profile.
Yeah. Okay.
Yeah.
And is there a length scale associated with this spin?
So essentially what is happening here is that if you look at what is the structure of the quasi-particle and quasi-hole here, the quasi-particle and quasi-hole are right on top of each other. But they do have a finite magnetic length scale dependent structure.
I see.
So there is some density profile to that excitation, exactly.
One more question.
Some silly this thing. You have shown the Hamiltonian, somewhere I might...
Yes, just Coulomb Hamiltonian. Nothing.
But when you put the spin, how does it go?
So I'm working everywhere with Zeeman equal to 0. if you now, to everything you can add g times mu b, and then that is the only, it's like a constant shift in Zeeman, which just counts how many down spins are there. That's all, yeah.
Okay, in interest of time, let's close the talk. Okay.